Good morning, everybody. Today's topic is rotation and angular momentum. Today we are going to learn the rotational variables such as angular position and angular velocity, angular acceleration. And then we will also learn the rotation with a constant angular acceleration. And then we will understand what is moment of inertia and the rotational kinetic energy. Then we will calculate the moments of inertia of some simple objects. And then we're also going to learn the angular momentum, which is closely related to the linear momentum, but angular momentum is related to the rotational motion. So first, let's look at the angular velocity. Now, let's look at a uniform circular motion. A particle moves around this circle with a constant velocity. The velocity of the particle is equal to v, and the magnitude of the velocity doesn't change. So this kind of motion is called uniform circular motion, which we have also already studied this motion earlier. Now let's denote this angle as theta. This is the angle between the radius vector r and the x-axis. And so the angle theta is called angular position. As the particle moves in its circular path, it also traces an arc length s, and let's denote this length as s. So there is a relationship between r, s, and theta. So theta equals to s divided by r. The units of theta is radian, so the units of theta radians. There are 2 pi radians in 360 degrees. So far we have talked about the angular position, and we denoted it as s divided by r, and by definition it's a scalar quantity, right? But we can also define a vector angle, which is theta, and this kind of vector quantity would be very useful when we work in the next definitions such as angular momentum. So the theta vector and s vector and r vector are closely they are related, as s vector is equal to, from this equation, if you find s, it's equal to theta multiplied r. So we can define a theta vector such that s multiplied theta vector, theta multiplied r vector, this is the vector multiplication, gives s vector. So now we can also define the angular velocity. The angular velocity is denoted by omega. And the definition of angular velocity it is the time rate of change of the angle theta, which means omega is equal to delta theta divided by delta t, and we can also define the instantaneous angular velocity, which means that omega instantaneous, let's call E. E means instantaneous. Limit delta t going to 0, delta theta divided by delta t. Sometimes we can also denote this as d theta divided by dt. Now, so as we have found that S was equal to R multiplied theta, and if we differentiate this arc length S with respect to t, which is d dt S would be equal to d dt r theta. So in differentiation, there is a multiplication of two functions. So the differentiation would be d dt r multiplied theta plus r d dt theta. Since in a circular motion, the radius vector r, the module of the radius vector is a constant quantity, so the differentiation with respect to t would be equal to 0, which means r doesn't change over time. So from here we can find that the tangential velocity vt, which is equal to ds divided by dt when r is constant, would be equal to r multiplied d theta divided by dt, only this term, so the other one would be equal to 0. And we also called this one as instantaneous angular velocity, so it would be equal to r omega. So I didn't write here I index, so anyway we will understand it without the index that it is an instantaneous angular velocity. Now if you consider disk, rotating with some angular velocity omega, let's consider these 2 points, the first and second points. After some time, these 2 points will come to this distance. So, which means even though their arc lengths are different, and also their radius vectors are also different, but the omega in this case for the first and second point, they are equal to each other. Well, in some motion, the angular velocity also changes. In that case, we have to define angular acceleration. So the instantaneous angular acceleration, let's denote it with some letter, which is alpha, which is called instantaneous angular acceleration. So instantaneous angular acceleration, which is limit when delta t goes to 0, delta omega divided by delta t. So the instantaneous angular acceleration is the derivative of the angular velocity with respect to t, which means d omega divided by dt. Since omega is a vector quantity, since tangential velocity v and omega is related as following, omega multiplied r. So since omega is a vector quantity, tangential, I mean the angular acceleration is also vector quantity, as we said, we can also write this equation as in the vector form, like this. So the tangential velocity of the particle in a circular motion is a vector product of the angular velocity with this radius vector. And if you take time derivatives of this equation, so take time derivatives, v vector would be equal to d dt. Here we have omega multiplied vector product with r. Since r does not change during the motion, it would be, so this gives us an acceleration, and the omega dt, as we know, gives us this angular acceleration. So a would be equal to alpha r. In general, this angular velocity is a vector which is parallel to the rotational axis, and its direction is determined using the right hand rule. Now let's look at the spatial case where the rotation with a constant angular acceleration. Consider alpha is a constant. Now, since alpha is a this angular acceleration is a constant, by definition, alpha is equal to d omega divided by dt. So we can find d omega from this equation, which would be equal to alpha dt. Now we will remember that this alpha is a constant velocity. If you take integration, so omega changes from omega 0, or we can also write from omega initial to omega final, and t goes from 0 to t. So initially, let's fix t0 as 0. So the left hand side gives us omega final minus omega initial, and then it would be equal to alpha multiplied t. So which is equal to, so the final angular velocity is equal to initial angular velocity plus alpha t. And this equation is very similar with the one in the translational case. So velocity of the particle, the final velocity is equal to initial velocity plus at. So this is our main equation so far. Now to find the final angular position, theta final. So we have to remember the definition of omega. So omega was equal to d theta divided by dt. From here we can find that d theta is equal to omega dt. So we know that, so this is the final, let's put final, and the final angular velocity is equal to initial angular velocity. So initial angular velocity is a constant number. The final angular velocity, on the other hand, depends to time, so it is alpha t multiplied dt. Now if we integrate both sides, so theta changes from theta initial, or sometimes they use theta 0, to theta final, and we can also integrate on both sides, so t goes from 0 to t. Now theta final minus theta initial would be equal to, so since omega initial is a constant quantity, we can take this out of the integration. So v initial t, so this theta is also a vector quantity, plus alpha is also a constant quantity, so it also goes to out of the integration, and then we have t dt, so it gives us t squared divided by 2 from 0 to t. So again it remains the same. We can write our final equation as the theta final would be equal to theta initial plus omega I t plus alpha t squared divided by 2. Now we are going to look at some problems. We are going to solve some problems here. So the first problem, a deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from his fishing reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.5 centimeter. So r is equal to 4.5 centimeter. So this is our first exercise. From its axis of rotation, the reel is given an angular acceleration of 110 radians per second square. So angular acceleration is also given, which is equal to 110 radian per second square, and for 2 seconds, t is equal to 2 seconds. What is the final angular velocity of the reel after 2 seconds? So we have to find the final angular velocity. To find final angular velocity, we have to use the equation which we have derived here, this one. So final angular velocity is equal to initial angular velocity plus alpha t. So initial angular velocity, initially the system was at rest, and then so it is 0 plus alpha is equal to 110, t is equal to 2, so it's 212 radian second. So moment of inertia and rotational kinetic energy. So any moving object has kinetic energy, even though it's rotational. However, so far we do not know how to calculate it, right? We know that in translational motion, the kinetic energy of the particle is equal to mv square divided by 2, or we can write m divided by 2 v square. However, for a rotating rigid body, it is complicated. We cannot write the rotational kinetic energy in this form. Why? Because for a rotating rigid body, every point of this object has different velocity. So from point to point, v changes. And to write kinetic energy in terms of v is a little bit complicated. However, in rotational motion, for example, when we consider the disk, rotating disk, angular velocity was the same in each point, so omega is constant for a rigid body. So we have to find a way to write this kinetic energy in terms of omega, not in terms of v. If it's a single particle, for example, rotating around some rotational axis, we can write this energy as E is equal to, which is mv squared divided by 2, and since v is equal to omega r, we can write it as m r squared divided by 2 multiplied omega square. However, in a rigid body, there are so we can divide this rigid body into smaller pieces. So each of the small piece has its own velocity, and let's put index for each quantity to denote that this mi is the mass of the one of the small pieces of the rigid body. So, and similarly, ri and omega I, this is the ice particle. So the total energy would be equal to m divided by 2 r square multiplied, well, it is omega square, right? So I have to put here I and sum them. And we will get 1 divided by 2 summation mi ri square multiplied omega I, and omega I is constant for each particle, and let's denote it as omega. So you see, this is the total kinetic energy, rotational kinetic energy, and this equation, we have to find it to write this equation in a more convenient way. So to do so, we have to denote this with some letter. Let's call it I. This I, which is equal to summation mi ri square, called moment of inertia. Then we can write the rotational kinetic energy as, so it was equal to 1 divided by 2 summation mi ri square multiplied omega square. Since this quantity is equal to I, we can write it as 1 divided by 2 I omega square. The units of the rotational kinetic energy is still joule, and the units of moment of inertia is kilogram meter square. Now let's look at the following common shapes. The first one, hoop. And consider that this hoop is rotating around this x-axis with some angular velocity, and consider that this hoop has a mass m and a radius r. Then the moment of inertia of this hoop I is equal to m r square. If this hoop rotates around an axis which passes through any diameter, let's call this y, then if the hoop rotates around this axis, then the moment of inertia of this axis is equal to 1 divided by 2 m r square. Again, the radius of the hoop is r, the mass is m. Now consider a solid cylinder, for example this one. About this axis, let's call it x, and this cylinder rotates around this axis. Consider that this cylinder has mass m and the radius r. Then the moment of inertia of this cylinder is equal to 1 divided by 2 m r square. A bit later we are going to derive some of these quantities, not all of them, but some of them. If this solid, now consider this solid cylinder around this axis. If it rotates in this direction, then we can write it as well, I would be equal to 1 divided by 4 m r square, plus, again I can write plus 1 divided by 12 m r square. Then now consider a rod. This one, thin rod, which has a mass m around this y-axis. Then this rod has angular, the moment of inertia, which is equal to 1 divided by 12 m r square. If we consider this rod, the rotation of this rod around this axis, then the moment of inertia would become 1 divided by 3 m r square. Now if you consider a solid sphere, around an axis which passes through any diameter, then the moment of inertia would be equal to 2 divided by 5 m r square. And if we consider a sphere thin sphere, then I would be this is a thin spherical shape, and it would have 2 divided by 3 mr square. So from these two equations we can conclude that if these two objects has the same mass m and m, it would be more difficult to rotate a thin sphere compared to this solid sphere. Now let's look at some simple examples. The first one, the most simplest one, let's take a massless rod, and at the end of them there are two masses, each have a mass m. The length of this massless rod is L. So first we have to find its moment of inertia about this axis, which passes through the center of the rod. Then both sides has, so this first, let's call this first particle, and this is the second particle. The distance from first particle to the rotational axis is L divided by 2, and the second one is also the same, which is L divided by 2. According to the formula, I is equal to mi ri square. So there are only two particles, so I can go from 1 to 2, m1 r1 square plus m2 r2 square. m1 and m2, they are equal and they both have mass m. r1 is equal to, well, r1 is equal to L divided by 2, and this is also the same for r2. So L divided by 2 square plus m L divided by 2 square. So the summation would give us 2m L square divided by 4, which is equal to 1 divided by 2 m L square. Now let's find moment of inertia around the axis which passes through one of the masses, through this axis. Then I would be equal to the first particle, so again it is summation of mi ri square, so it's m1 r1 square plus m2 r2 square. The first one has zero distance from the axis of rotation, so it is equal to 0, plus the second one has mass m multiplied r2 square, the distance from the second particle to the axis of rotation, so this is equal to L. So I have to put here L square, so it is mL square. The next problem, consider a hoop. For example, this one, which is rotating around this x-axis, and the radius of the hoop is r. If we draw it from a different angle, so it looks like this around this axis, which is perpendicular to the plane, horizontal plane, then each particle, for example, let's call it dm has the same distance from the center of rotation, from the rotational axis. So I can write I as dm multiplied r, or let's call it di. And if we integrate it, I would be equal to r dm, which is equal to, since r is a constant quantity, it is r multiplied m. Okay, so this is r square, right? Sorry, so this is r square. So we will get m r square result. Now consider a uniform thin rod, and we are going to learn its rotation around this axis. Let's call it y. And since this rod is a uniform, we can also define a linear mass density lambda that is equal to m divided by L. L is the total length. Let's call it total length of the rod. So from this equation we can see that m is equal to lambda L. If we say that this direction is the x direction, if we integrate, if we take differentiation, then dm would be equal to lambda dl. Since lambda is constant, we will get lambda dl. dl is this part, or we can also call it as dx since it is x direction. Let's call it, so dl is equal to dx. So I can rewrite it as lambda dx. And the distance from this point particle, I mean from this piece dm element to the rotation of to rotational axis is x. So the moment of inertia of this dm point is equal to di, which is mass dm multiplied the distance square. The distance is x square. So inserting dm, which is equal to lambda dx, so we'll get lambda x square dx. To find I, you have to integrate both sides, so it's equal to di. So lambda x square dx. X changes from this one is minus x, minus, so the total distance is L divided by 2, so the this is minus L divided 2, so this one is L divided by 2. X changes from minus L divided by 2 to L divided by 2, and we will get lambda x cubed divided by 3, from minus L divided by 2 to L divided by 2. It is equal to lambda, so I can write 2 multiplied, and also we have 1 divided by 3 and L divided by 2 cube. So it's equal to lambda L cube divided by 3 multiplied 4, so which is equal to 12. And I can also write it as lambda L multiplied L squared divided by 12, and this quantity gives us the mass of the rod. So it's equal to 1 divided by 12 ml square. So I is equal to 1 divided by 12 ml square. Now again, if we consider this problem, but if we take the rotational axis as this one, which passes through one of its ends, let's call this y-axis, and this one is the x-axis, then again we have to take dm element here. So this is dm element, as we have found above. Dm was equal to lambda dx, and di would be equal to dm multiplied, so again the distance square, so this is the distance, which is equal to x square, so it would be equal again lambda x square dx. However, this time we have to integrate lambda x square dx from 0, x changes from 0 to L. So the boundaries goes from 0 to L, and then we will find lambda x cubed divided by 3 from 0 to L, and it gives us 1 divided by 3 lambda, okay, let's write it, lambda L cube. So I would be equal to 1 divided by 3 lambda L cube. Now let's calculate the moment of inertia of a rotating disk. So this is disk, and it's rotating around this axis, which is perpendicular to this plane that contains the disk. As we have seen that the moment of inertia of the hoop is equal to di, which is equal to dm, okay, so dm multiplied r square. For the hoop it's equal to mr square, right? In general we can write. So we can divide this disk into small hoops, coaxial hoops. Now let's take one of the hoop, which is located from the center. The distance from to this hoop is equal to r, and the mass of the hoop is equal to dm. Then the inertia, the moment of inertia, di, would be equal to dm multiplied r square. So now the dm is equal to the mass of the hoop. It's equal to, it's proportional to the lengths. For example, okay, this is, let's draw it below. So we are looking at this hoop. Okay, so this is how it looks like, and the width, this one is dr, and the circumference is equal to 2 pi r. So the surface, the area, is equal to 2 pi r multiplied dr. So and I have to also multiply it to the surface density, right? Let's call it sigma, and sigma is constant for in every point of the disk. So we will get 2 sigma pi r dr. Then the di would be equal to 2 sigma pi r dr multiplied r square. If we want to find the I itself, it would be equal to di, so 2 sigma pi r cube dr. So r goes from 0 to r. The integration will give us 2 sigma pi. It is r4 divided by 4 from 0 to r. So it gives us 2 sigma pi r4 divided by 4. We know that the total mass m is equal to sigma multiplied p r square. So we can write it as sigma p r square multiplied r square divided by 2, and we will get, let's erase this part. This is, so this one is equal to m, then we will get 1 divided by 2 m r square. So now we are going to look at some problems. The first problem, a 25 kilogram child, the mass of the child is equal to 25 kilogram, stands at a distance r, which is equal to 1 meter from the axis of a rotating merry-go-round. The merry-go-round can be approximated as a uniform solid disk with a mass of 500 kilogram and the radius of 2 meters. We have to find the moment of inertia of this system, I total. So this is a solid disk and it rotates around this axis with some angular velocity. Since the disk, the merry-go-round, has mass m, which is 500 kilogram, and let's consider that a boy is standing here, which has a mass m. The radius, the distance from the rotational axis and a boy is r, and the radius of the disk is big R. First, let's find the moment of inertia of the boy, which is equal to mr square, and the moment of inertia of the disk, let's call it I2. This is 1 divided by 2 mr square. So the total moment of inertia is equal to I1 plus I2, and I can write it as mr square plus 1 divided by 2 mr square. M is equal to 25, R is equal to 1, plus 1 divided by 2, big M, 500 kilogram, R is equal to 2, so R square is equal to 4. 1000 plus 25, then we will get 1025 kilogram. The units of the moment of inertia is kilogram meter square.